The next topic we're going to talk about is nuclear fusion. This is the process that occurs inside of all power plants across the world, and effectively how it works is you've got a highly unstable particle. Let's say uranium is typically the one that's used. And what happens is it splits into lighter elements when a high energy neutron is shot at it. It'll increase the mass of the uranium can no longer be stable, and it breaks apart into lighter elements. When it breaks apart into lighter elements, energy is released as a result in the form of radiation, in forms of heat. Now in a power plant, what's basically happening is the heat being produced boils water, this water turns a turbine, and then we get electricity. So let's picture what this would look like. So this example right here, we've got uranium-235. It's stable right now. If you take a look at the graph here on the bottom. That's not going to let me draw. So what happens is we're going to shoot a neutron at it. When we shoot a neutron at it, it becomes uranium-236. Uranium-236 is not stable. It's high of energy, so it breaks apart into smaller elements. Now how this would basically work in a nuclear reaction is we take a look at a chain reaction. We shoot a particle at uranium-235, and it breaks apart, which in turn breaks apart other things. And it causes a chain reaction. This chain reaction is what lets the energy out. Now, if we want to picture what this would look like if we were in a nuclear reactor, you have some particle. What these are chambers, and they hold the nuclear material. And if you take a look here in the top right-hand corner, you're going to see a thermometer. This gauges how hot it is. So what we're going to do here is we're going to fire neutrons in the particle. And we can see there's some breaking apart in the second column. If we keep firing particles, we'll see it starts to break apart. Now, if you take a look at the columns on the left-hand side, or on the right-hand side, you're going to see power output and the energy produced. The more often I hit firing the neutrons, the higher the power input goes, the amount of energy produced, but the temperature also increases as well. And you can see it starts to warm up too much. And this is what happens when we have nuclear meltdown occurring. This is why reactions have to be cooled at all times. Now back to the mathematics of how nuclear fission works. It's the same rules as every other nuclear reaction. The mass on the reactant side, or the left side, has to equal the mass on the product side, the right side. So you can see mass and protons here are equal to the mass and the protons right here. Let's try an example. I'm going to give you an unknown element. And when this unknown element is bombarded with a helium particle, it becomes unstable, and as a result, what's produced is this. We have acetine and 2 neutrons. Take a moment and try to figure out what the initial reactant is. If we take a look at the right-hand side, we want to figure out the total mass. Now we know the total mass is 211 plus a neutron plus another neutron. So that means the total mass is 213 for this side. On the left-hand side, we know the total mass has to equal 213. We know the alpha particle has a mass of 4, which means this unknown particle has to have a mass of 209. Same thing with the number of protons. We know acetine has 85 protons. We know the helium particle has 2 protons. Therefore, our new product has to have 83 protons. If we take a look on our periodic table, that becomes bismuth.